populated, we now have to group the cells together. We can group cells in combinations of one cell on its own, two cells together, 4 cells, 8 cells, 16 cells, and so on to the power of 2. This allows us then to provide a minimized expression for the overall system that we're creating. So in our Karnaugh map, we can group adjacent cells together. We couldn't, for example, group these cells together because of the 0 that's present. We could group these cells together, but we also have to maximize the amount of cells that are in a group. So in this case, that would be the maximum that we could create. We couldn't, for example, create a group of 3 because it's not a power of 2, or a group of 6, even if that was a 1 there. We wouldn't be allowed to group them together. We can also group adjacent cells that roll around or wrap around. So this table wraps around. So this edge, if you can imagine, is connected to this edge. So if there were 2 cells here, let's say for example there was a 1, 1 there, we could group these 2 cells and these 2 cells together to create a new group. In our case, there's not a 1, 1 here. So this is the grouping that we have to perform. We can also overlap groups together, and you should overlap groups to maximize the coverage of your groupings. So here's the first obvious grouping that we'll color this and say, well, that's one of the groupings. We've got 4 cells grouped together, and there's nothing to wrap around. There's no more adjacent cells that can be included in the group. We also have another group here. Now you can see that this one here is present in both this group and this group, but that's fine. So we can have 2 groupings that overlap. So I'll just group them together, and bearing in mind that this one still remains within the blue grouping as well. So that's it covered. We've covered all of our states in our Karnaugh map. So this is our minimized expression. It is possible that we would also have terms like a don't care term, where it doesn't matter whether it's a 0 or 1. If that's the case, we can use it if we want to, or if we don't want to, we don't have to use it. So there is a possibility of a don't care term as well. So what have we got? Well, our final expression f now equals the sum of products. So let's have a look at our particular grouping here. We can see, well, if we look at the blue grouping, which is these 4 cells together, we look for what has not changed along the rows and the columns. So if we look here along the AB column, we can see, well, A is present in its inverted and non-inverted case, but B is only present in its positive or non-inverted case. So this means that we've got B is part of one of our products. If we look at our row for the same blue grouping, we can see, well, 0, 0, 0, 1, 1, 1, 1, 0. So we can see that C is present in its non-inverted case in both of these columns, but D changes, so therefore we don't include D. So this means that we've got BC, and that describes the blue grouping. So B and C is the grouping of the blue group. We also have the green, and this is a sum of products, so we could say OR, and then we have our green grouping, and we could see, well, let's look at here again. What doesn't change? Well, we see that the A doesn't change, but the B does, so therefore B is excluded. And we look now along this row here, and we see that, well, the the C changes, but the D doesn't change. So we have this green grouping described as AD. And that's it. We've included all of our cells. So the minimization of this particular circuit is BC or AD, and that's the minimized version. So Karnaugh maps are a very efficient way of reducing quite a large number of states down. Providing you get successful grouping, it is possible that there is no minimization possible to Karnaugh map, but at least then you're sure that you have the minimum expression available for you. So this has provided a formal and quick way of reducing our minimization. It means now that our implementation only requires 2 AND gates and 1 OR gate. Now that we have our minimize function f equals AD or BC, we can take that function and implement it using our chips. So
here I've got my my 4 switches. We'll call them A, B, C, D, and we have them in pull down configuration. So you can see the resistors pulling down to ground. The outputs of these switches, or the values of these switches, are these grey lines here. So this is A, B, C, and D, the grey wires, and then we have our 7408, our AND gates, and this you can see we've powered to high and ground. We have our voltage regulator here, making sure we're getting 5 volts, and you can see it's powering this LED here just to indicate that we currently have power. Then we have our OR gate, so the output of our AND operations goes into the input of our OR gate. So you can see here that the first function is F equals AD, so A and D. So you can see A and D going into the inputs here, A and D, and the output here, the blue wire, is going into the first pin of the OR gates, which is the input of the first OR gate. And also we have our B, C is the input to our second AND gate. You can see the second blue wire going in as the second input to our OR gate. The green wire coming out then is our output, and we're using this to drive an LED just to indicate when the states are high. So again, the problem was to design a circuit so that the output, the LED, is on if the outermost switches are pressed, or the innermost switches are pressed, or 3 switches are pressed, any 3 switches are pressed at the same time, or all 4 switches are pressed at the same time. So you can see it's working so far in that it's not supposed to be lit if there's no switches pressed. So we'll try one switch. I've pressed each one of the switches and there's no output, which is correct. I can also try the 2 switches on this side, and you can see we get no output. On the 2 switches on this side, we get no output. So again, we were supposed to design it that if the 2 outermost switches were pressed at the same time, we should get an output, and you see we do. Or if the 2 innermost switches were pressed at the same time, we get an output, and we do. And then we can try 3 switches. So there's 3, and the second 3. Or if we try different, if we try a different tree, you can see that we get working there. Or if we try all 4 together, we get a perfectly functioning circuit.
The second part of this question asked you to take the expression that you'd implemented using AND and OR gates and to implement it using NAND gates only. Now, straight away, as soon as you're asked to implement an expression like this through NAND gates or NOR gates, the first thing you should think about is De Morgan's theorem. Now, De Morgan's theorem looks like this, and this is the simplification. You've seen De Morgan's theorem elsewhere, but here's the basic rule for De Morgan's theorem. If you have an expression AB with a bar over the entire expression, it's very important that it's a full bar over the entire expression, you can break this bar, and in effect all you have to do is convert the sign from an AND to an OR, and that then gives you a NAND conversion to 2 negative OR components. So AB bar, as with a bar, you break the bar and you change the operator. Similarly, if you have a NOR B, well then you break the bar and then you convert the operator from an OR operator to an AND operator, so it becomes a negative AND. Okay, so that's the basis of De Morgan's theorem. Now, on first inspection, it doesn't look like, well, we don't have a bar to break. So the first thing we have to do is get a bar in place, and this is quite straightforward. If we have an expression f, well, f inverted and inverted again is exactly the same as f. So you can say in effect that f is equal to f double bar. So that allows us to write, well, we can write our expression like this. We can say, well, f equals AD or BC as before, and put a double bar over the entire expression. And it's very important that you note that there's a double bar over the entire expression. Now we can apply De Morgan's theorem quite straightforwardly, and that allows us to break the bar and the lower bar. So if we break the lower bar, we can see that the lower bar breaks and the operator changes. So the the OR operation becomes an AND operation. So you can see that this is A NAND D, B NAND C, and then the overall output of those two NANDed operations becomes a NAND operation as well. So you can see now that it's possible to build this circuit using 3 NAND gates only. So we've gone from an OR gate and AND gates to a situation where we only need NAND gates.
So I also asked you to implement this circuit using NAND gates only, and as you can see from the minimization, it works out quite straightforwardly. We can get by with only 3 NAND gates. So the function becomes f equals a NAND D, NAND NAND B NAND C. So the first NAND gate is A NAND D, and the second NAND gate is B NAND C. So we take the output of that and then we apply it to a third NAND gate, so it becomes the overall NAND of those two functions. So here you can see I've just wired up the NAND gates, VCC and ground. I've connected up the yellow to A, the white to D, the blue to B, and the green to C. And this gives us our, you can see here, the first two inputs, the yellow and the white, go into the first 2 pins of the NAND gate. The third pin is this little green wire here, which goes as the first input into the third NAND gate. And then into the second NAND gate, pins 4 and 5, the blue and the green go in there, and the grey wire then becomes the second input into the third NAND gate. Finally, we have a resistor coming from the output of the third NAND gate, which then goes to ground. And you can see here that we get the exact same outputs for all states. So you can see for no input, we have no lights. Press one of each of the LED buttons, no output. We press the outermost, the 2 buttons on this side, no output. The 2 on this side, no output. Now, for our positive state, for our high states, press the 2 outermost buttons. You can see that both LEDs light. The 2 innermost buttons, you can see both LEDs light. And similarly for any 3 buttons then that we try, and then all 4 buttons together. So you can see that the 2 circuits are exactly equivalent. On this side we have only used 3 NAND gates, and on this side we're using OR and AND gates.
If we were asked the question to implement the same expression using NOR gates only, well, we would follow a similar procedure. In this case, we can look at the expression and we can say, well, let's invert the individual components of f. So AD double bar is equal to AD. So we haven't changed the function, the output, or the way this particular expression behaves. So by putting in a double inversion under each individual components, then we can apply De Morgan's theorem as before. Break the bar. You can see AD, break the lower bar, becomes A NOR D, and we've still got the upper bar, the inversion there, and we're still not quite finished. It might look like we're finished, but you see then here in the middle we've got an OR operation, not a NOR. We've got an OR operation, so we still have to finish this off. And the easy way to do this, well, you should have an idea from before, is you can see, well, we can just add in a double inversion. Now the inversion itself, it's relatively straightforward to create an inverter from a single NOR gate. So you can see in this case we've got a NOR operation, inverted inputs, so we have to invert the inputs, and we've also got a double inversion. So we need quite a number of NOR gates for this particular implementation.